Kia ora team, welcome to our first part of biomechanics, so a new topic. What we're going to do is look at the difference between what the terms biomechanics and kinesiology are. They're often used interchangeably and that's okay, but there are some subtle differences. We're going to look at qualitative and quantitative biomechanics, so two different ways that a biomechanical analysis can be presented. We'll chat about anatomy, which is something that you know lots about already, but then we'll look at what functional anatomy is. Linear versus angular motion, so how objects, people, segments of the body move and how we describe those. And then we'll look at different ways of analyzing biomechanical movements, the forces that produce those movements in terms of kinematics and kinetics. And then we'll look at difference between statics versus dynamics. So there are a couple of trail guide to the body human movement videos. I've added these links into Moodle, so what you might want to do is pause this and go check out that part 1 video, little intro video. So biomechanics and kinesiology. So kinesiology you may have heard of before. It's the scientific study of human movement, and I guess the key difference is it's an umbrella term, meaning that it encompasses or covers a lot of different things. So it's a term used to describe any form of anatomical, physiological, psychological, or mechanical human movement evaluation. So how we evaluate how somebody moves in terms of their anatomy, their physiology, and their psychology. Kinesiology also describes the content of the class in which human movement is evaluated by examination of its source and its characteristics. So source meaning where did it come from? So the content will be measured in a way of where did that movement come from, and then also what does that movement look like. So if you think about mechanics, the word mechanics, I think of machinery or mechanical movement. So mechanics is used originally by engineers to design and build structures and machines. Mechanics provides a tool for analyzing how strong a structure is, which, if you think about construction, strength and being able to handle force is really, really important. But also ways of measuring the movement of a machine, or predicting how that machine might move. If you have an idea or a concept, mechanics is a way of predicting through measurement or observation how that machine might move and what kinds of forces it might produce. Biomechanics is the study, so bio and mechanics together is the study of the structure and function of the biological systems. So biological systems is that structure of organization that we looked at in HAP, where we build an organism from cells. So we're using the method of mechanics to help study the structure of biological systems. The study of forces acting on and generated within the body and the effects of these forces. So what forces act on us, what forces are generated by us, and what is the effect of these forces, and specifically what is the effect of these forces on things like our tissues, fluid, or other materials used to diagnose things, so injuries, illness, to then provide treatment, or also for research purposes, so to learn more. So in your own context, it's sort of about understanding what applying force to different tissues of the body produces, how you can use your own body to increase the amount or decrease the amount of force that you might want to use, understanding how force in our environment affects individuals' tissues, so that you can diagnose or understand, not so much diagnose, but understand how an injury has happened, or how physical stress is happening or manifesting on the body. It then also helps you to understand how you might design your treatment around that space. Qualitative versus quantitative biomechanics is two different ways that biomechanical information can be presented. So qualitative, I think about the word quality and a description of that. So it's describing movement based on what you've seen, what you can observe. So you often do a qualitative assessment on a client by looking at their static posture and looking at like scapular levels and pelvis levels and alignment based on a vertical imaginary line, observing shapes that you see based on what is normal from what you understand is normal in terms of static posture or dynamic posture too. Whereas quantitative means some aspect of your analysis is going to be measured. Quantity, that's the word I think of when I think of quantitative. Quantity, numbers, it's always got something to do with actually getting a measurement. So it's a lot more specific, whereas qualitative is a bit more subjective or descriptive. In such an approach of quantitative analysis, the motion characteristics, so the characteristics of the motion that you're measuring of a human body or an object, so it could be something that is thrown, for example, is described using parameters such as speed, what direction it went in, how the motion is created through the application of forces, so looking at angle changes, measuring the amounts of force that are actually produced, and this could be both inside the body, so around joints, but also outside the body, so measuring force that is put into a projectile, for example, like a shot put. But then also you can use quantitative measures to look at optimum body positions and actions for efficient and effective ways of moving. Anatomy versus functional anatomy. So if you think back to HAP, anatomy is the science of structure. So what does the body look like? What's it made up of? Labeling, knowing the names of different anatomical positions within the body. It's the base of the pyramid from where the expertise of understanding human movement is developed. So that's why, if you think about how you've been scaffolded within content, understanding like what the skeleton looks like, the muscles that move the skeleton, the structure of muscles, how is that foundation of understanding movement in action, which is functional anatomy. So functional just means purposeful movement. So in the exercise space, functional training is like the in vogue, and often it's a term that's thrown around and I think misinterpreted a little bit. Like for me, functional just means any kind of movement that has some kind of function. So like machines get a bad rap in the gym. However, they provide function. A bodybuilder, their goal is to build muscle. A part of that is to put muscle under stress over time. That increases. There's only so many ways of doing that. Using machines in the gym is a functional way for that individual to meet the outcome of what they're trying to achieve. So functional movement generally means applying to everyday running, walking, lunging, bending, daily functions, but you can pretty much find function in any kind of movement. Using a functional anatomy approach, think to yourself, how can I describe the lateral arm raise using a dumbbell? So using your understanding of anatomical terminology and describing what movement looks like, describe what a lateral arm raise with a dumbbell would look like. So things like what joint actions are happening, what muscles are contracting to create that movement. Then we've got this idea of motion. So motion, if you think of motion sickness, people can get sick based on moving around. So movement or motion is a change in place and position. So you either move from one position or one place to another, or a change in what your posture looks like over time. Time could be really, really short, so a change in posture from seated to standing, or it could be a change in posture over time, like a lifespan. Think about if you could take a snapshot of your standing posture every day in your life and watched that and fast forward what that might look like. There's two types of motion that are present in human movement, or when an object is being propelled. So I think of propulsion as like us moving something like a shot put or a javelin or a ball. So we've got this idea of linear motion, and that's a movement in a straight line. So think linear, straight line. The line can also be curved, but the idea is that every point within the body or the object is moving at the same distance or the same speed at the same time. So you running around a track, if you keep your speed constant, that's linear motion, because every body part is moving at the same speed. Center of mass of the body is often what's used to measure that point in a linear analysis, because obviously, like I mentioned, running, there's actually parts of the body that are going through a different type of motion, but the center of gravity of your mass is moving the same speed. This is the point at which the mass of the object appears to be concentrated, so that's our center of mass, and it represents the point in which the total effect of gravity acts on that object. So it means that gravity has its full force in that center of mass of that body or that segment. And that moves based on what your body is doing. So you move your mass around, that will change your center of mass or center of gravity. The next one is angular motion. So if you think about angles, it means not a straight line. It means some kind of bend. So angular motion is a movement around some point of axis. So it has to be some point of rotation. So there's a center point where something is moving around it, with that center point being like the pivot point. So it's not just moving in a curved line, it's actually moving around an axis. And the key is the different regions of the same body segment or the same body are covering a bigger distance or a different distance in the same amount of time. So like if you were to do a pirouette, so to spin around with your arms out to the side, your hands move in cover a different amount of distance compared to the medial aspect of your body, but it's all done in the same amount of time. So if you think about speed or velocity, your hand is actually moving much quicker than the center. It is typical in biomechanics to examine the linear motion characteristics of an activity and then follow up with a closer look at angular motion that create or contribute to that linear motion. And what this really means for us is that all linear movement of the body, so for us to move from position to position, is generally a linear motion, but we are propelled through a sequence of angular motion around every single joint. Because if you think about the articulation of our skeleton and muscles pulling, we're actually always creating this angular motion around every joint, which creates linear motion of our center of mass. So often in human movement, we might be measuring linear motion as a global look of movement, but what's creating the forces to generate that linear motion is actually coming from a series of angular motion within our joints. Kinematics versus kinetics. In a biomechanical analysis, these can be conducted from either of two perspectives. One is kinematics and the other is kinetics. So kinematics, underline the M part, the matics part. I think of matics as movement, and movement we can see. That's pretty much the key thing to take from kinematics, is movement that we can see. It's concerned with the characteristics of motion from a spatial, so movement within space, and temporal perspective. Temporal means time, so what we can see and generally over time. Kinematic analysis involves a description, so describing movement to determine how fast an object is moving, how high it goes, or how far it travels. These measurements such as like describing position, velocity, and acceleration. So yeah, what does the movement look like? What can we see? Kinetics, in terms of a biomechanical analysis, is the area of study that examines the forces that create the movements within a system. So things that we can't see. So the previous was things that we could see. So you're describing like stride length, stride frequency in a run. Kinetics would be, okay, what's the amount of force that has been generated during every foot contact with the ground. You can't actually see that force, but you can measure it, and that's a kinetic analysis. A kinetic movement analysis examines the forces creating this movement. It's more difficult than a kinetic analysis to both understand, to comprehend, and evaluate, because you can't see those forces. And a force is not something that is really tangible and can be described in more than one way. It's the effects of those forces that can be observed, and that's what kinematic analysis is. When the force is applied, what does that look like? So things like force, linear and angular. Torque is the term for angular force. So angular motion is created by torque. Statics versus dynamics. If we think about static stretching and dynamic stretching, which you may have heard of, static is still, dynamic is moving. So statics is a branch of mechanics that examines systems that are not moving or are moving at a constant speed. So like if you were sliding down a hill, but still, that's still a static position. These static systems are considered to be in equilibrium because there's no acceleration. So everything is the same. So even if you're moving, the movement is the same. And this is because the forces that cause this object or person to move, or the forces that cause this person to speed up, to begin moving, to overcome what's called inertia, or to slow down, are neutralized by the opposite forces, so they cancel them out. So the forces that are generated to speed up and to or to slow down are the same as all the other forces, like air resistance. Everything is equal. What I just said before will make a little bit more sense when we look at some of Newton's laws. So like action and reaction, where the amount of force applied is opposite and equal to the amount of force received. It's easier to hold the arm out. This is a question to think about. Why is it easier to hold your arm at your arms at your side? So if you think about static posture and holding your arms at your side, than it is perpendicular. Perpendicular is this, so 90 degrees to a straight line. Why is it easier? And if you think about static posture, the most efficient static posture in terms of reducing the amount of force that we need to apply is when body parts are stacked on top of each other. As soon as you put your arms out perpendicular, there is force being created. Everything is still, but there's force being created against gravity. So why it's in static equilibrium is the amount of force that the deltoids need to create to hold your arms up matches the amount of force that is opposing the deltoids through gravity. Put our arms at our side, then our body is stacked in a way where the center of mass is closer to the point of where gravity is pulling on us. If you think about like spine, lordosis, which is a big arch in your lumbar spine, or scoliosis, which is this curved spine. Thinking about this concept and deltoids having to overcome more force against gravity, what do you think the effect of having like a unneutral spine might have on the muscles that create stability through, like a static posture in your torso, and what happens to the rest of the body to compensate for that? Because statics involve no change in the kinematics of the system, so the movements that we can see, a static analysis is usually performed using kinetic techniques to identify how much forces and the site of where that force application is happening for maintaining posture, for maintaining position, or for maintaining speed. So if you think about, even if we go back to the idea of mechanics and building structures, understanding where force is being applied to hold a building in a static position. So, you know, skyscrapers go straight up and down. If you put it on an angle, that's going to change how the structure needs to be built in order to maintain that, to overcome the force that is now going to be greater as the center of gravity moves. Dynamics is a branch of mechanics used to evaluate systems that are being accelerated. So this is where velocity is changing, and we are increasing the amount of velocity that's being created through different segments. Dynamics uses both kinetic and kinematic approaches to analyze movements. The analysis of the dynamics of an activity such as running may incorporate a kinematic analysis. So kinematics means what does it look like? So what is the cadence? How many steps have been made? What is the stride length? How far is that? What is the time off the ground? And then from there you can also do a kinetic analysis that describes, okay, so with that stride length, stride frequency, how much force is actually being generated from the ground, and across all the joints that contribute to running. So just to try and simplify that, kinematics would be what does the movement look like? So what are the different angles of the body when it's moving? How many steps are we creating? How often are we doing that? What is our time, our contact time on the ground? And then the kinetic analysis would be, okay, so how much force is being applied to the ground? What force is being generated at the muscles? Here's a bit of a schematic of pretty much what we just covered. Kinesiology is that umbrella term. Biomechanics is a little bit more specific to mechanical movement. And then we've also got functional anatomy on the side there also, which is a way of describing movement. And then under biomechanics, it gets a little bit more technical with our kinematics, which is describing what we see. And we've got either linear or angular movement, things like describing position, velocity, acceleration. And then kinetics, also linear and angular, but we're describing the amount of force, and in angular, it's the amount of torque. This is a bit of a recap from what you already know. Anatomical movement descriptors. So some of the stuff that we've covered in the past in terms of joint actions, and you know, I've always said understanding how the skeleton moves is really, really important. Here's a bit of a recap and an extension. So segment names, skeleton, we've got the axial, which is the center, so the skull, the spine, the ribs, and then we've got the appendicular, which is your limbs, including the girdles that attach your limbs to your axial skeleton. So that's things like your scapula and your clavicle for your shoulder girdle, and your pelvis for your legs. Anatomical terms, which you know, anatomical position, you've got superior, inferior, posterior, anterior, medial, lateral, proximal, distal, so we get that. And then we also understand the basic joint action terms. There's 6 basic movements, and then there's varying versions of those which you know. So flexion, extension, adduction, abduction, and then left and right rotations. Something that we haven't talked about is planes and axis. The universally used method of describing human movements is based on a system of planes and axes. So we move through different planes, and we move through or rotate through different axes or axes. A plane is a flat, 2-dimensional surface. It's like a piece of paper. There are 3 imaginary planes that are positioned through the body at right angles to each other so that they intersect at the center of mass. So here's a diagram. Sagittal plane, I think sagittal splits the body side to side. Sagittal, side to side. Frontal splits the body front to back. Transverse, also called horizontal plane, splits the body in half. So sagittal would be any movement forward and back so that you didn't come out of that plane. Frontal would be any movement sideways if you were stuck in, if that plane was splitting you in front to back. Transverse would be any movement through rotation. Um, the movement in a plane always occurs about an axis of rotation that is perpendicular to the plane. So we've got a plane which is 2D. Perpendicular means like this. So think of plane as being flat, axis of rotation being like a pin. So perpendicular. So if this was the plane of movement would be forward and back, but the rotation would be like this. Okay, so if we're looking at this, rotation, movement within the plane. Yep. So here's our diagrams again of our sagittal, frontal, horizontal, or transverse. If we put a needle perpendicular to that plane, the sagittal plane has a mediolateral axis, so medial lateral. The frontal plane has an anterior posterior axis, and then our horizontal or transverse plane has a longitudinal axis. So you can move along the 2D space and you can rotate around the axis. Alright, pause the video, go watch part 2. Position is describing where an object is in reference to something else. So here we've got a person on the top dive board. It's 10 meters high. The position is 10 meters above the water. Units of length are used to measure the position of an object from a reference axis. So this person is 10 meters above the water. Displacement versus distance. So these two both measure position change. Displacement is a measure in a straight line from one position to the next. So where do you start, where do you finish, how far is that distance? Irrelevant of how you got there. Displacement is defined by how far the object has moved from its starting position and by the direction it has moved. So it's describing magnitude, so how far, highlight that, and it's describing direction of change in position. So it's moved this far and it's moved this far in this direction. So it's called a vector. A vector quantity is a quantity that represents magnitude, so how much, and then also direction, so where has it gone. Whereas distance is what's called a scalar reference, and it just measures the actual length of the path traveled. Both of these measure different things and are useful in different spaces. If you run a marathon, you'll want to know the total distance you cover to know when you're finished. Displacement would be, so zero displacement would be telling you that it's a loop track. So your position from start to finish is the same. And that's useful in different scenarios. Alright, so this slide is just to show visually what the difference is between displacement and distance. So we've got a person who has moved from top left corner to the bottom right corner. Their displacement is a straight line from first position to second position. But the path that they actually moved to get there was different, and it looks like this. So that was the distance covered. Velocity is a vector quantity as well, so it describes magnitude and direction. It's describing the rate of change in displacement over time. So how long does it take? So it's similar to speed as you would know it, but it also describes direction. So the equation for working out velocity is what is the displacement and how long did it take? Whereas speed is a scalar quantity, so it's just telling us how fast did somebody travel over a certain amount of time. So that is a similar kind of equation. Speed equals how much distance was covered divided by how long did it take. So we've got our equations up the top. I've got our same person. The displacement was 20 meters southeast. So if we look at our compass up the top right hand corner, never eat soggy Weet-Bix. This person has been displaced 20 meters in the direction of southeast. Distance though traveled was 100 meters. So it took them 1 minute or 60 seconds to travel that distance. If we use our equations, velocity was, so you go displacement of 20 meters divided by the time of 60 seconds. their average velocity over that displacement was 0.33 meters per second, which is slower than their speed. So their speed was 1.66 meters per second. So we went distance, 100 meters divided by the 60 seconds is 1.66 meters per second. So I guess one way to look at the difference is, imagine there was two people in the top left-hand corner. One person was going to cover the orange line and one was going to cover the blue, but the deal was they both finished in 1 minute. So the person running the blue line is going to have to cover that distance quicker compared to the person who was just following the orange line. So that's why the average velocity is slower than the average distance. Acceleration in human motion, the velocity of a body or a body segment is really constant, like rarely constant. So it isn't constant very often, if at all, really. The velocity often changes during a movement. The rate of change in velocity with respect to time, so how much that velocity changes within a certain amount of time, is called acceleration. In everyday usage, acceleration means to go faster or to speed up. But acceleration, because it's a vector quantity, refers to both increasing and decreasing velocities. So a positive acceleration is getting faster, a negative acceleration is slowing down. So in terms of like the human body, getting faster involves a lot of concentric contraction to generate force. Slowing down involves a lot of eccentric force production. So changing direction is a lot of concentric eccentric force. Because velocity is a vector quantity, so is acceleration. So we'll get into some equations here. I don't want you to get too confused with it. Really, it's like acceleration is a change in velocity over time, getting faster or slowing down. It's important in terms of understanding that, for example, concentric contractions create that speed up phase through our agonist muscles, and then slowing down is a lot of eccentric stuff. So running uphill or accelerating uphill, a lot of concentric contraction, then coming downhill and putting the brakes on, a lot of eccentric of the same muscles. Force is a very difficult concept to define. It's generally more of an idea of looking at what force can actually do. According to Newton's principles, objects move when acted upon by force. So something has to create that movement, and that force has to be greater than the resistance force provided by the object. So like a heavy rock with a big surface area on the base needs a lot of force to push it because of the forces pulling down by gravity and the forces created by friction. Whereas an ice cube that is small doesn't require a lot of force to move it. So the forces that are acted on something have to be greater for something to happen. A force involves the interaction of two objects and produces a change in state of motion. And remember, that can be linear or angular, and this could be through pushing or pulling. A force, therefore, may be thought of as an interaction, a push or a pull between two objects that can cause the object to accelerate either positively or negatively. Now, the thing with the body is, if you think about muscles, they don't do any pushing. So the force generated by the body is all a pulling interaction. What is the object that we interact with that is increases the amount of gravitational pull on us? And that's the Earth. And because it's so big, what the force looks like is greater on us than it is on the world. So when we interact with the Earth, every time we step, not much happens to the Earth because it's so big. The inertial force is so massive that we are unable to move it. But that force looks pretty has a great effect on us. Torque is force, is a type of force, but it's just describing rotational force. So opening up a bottle or twisting. Our muscles create force at a joint because we have this axis, a movement around an axis or a pivot point. When a force is applied such that it causes rotation, the product, so the product is like what happened, what is created of that force and the perpendicular distance. So that's like perpendicular, remember we've said this a few times, the perpendicular distance to its line of action is referred to as torque. So boom, torque would be this rotational pull. That if you change this perpendicular distance, that will actually change the amount of force that can be produced, and we'll look at levers next week. A torque is not a force as such. As we said, force itself is more of a looking at the effect, and the effect of force, if we're talking about torque, is that it causes rotation. So that might have sounded a bit confusing when it says torque is not a force. It's more force can create either like linear movement or angular movement. If we think about angular movement, then the word that describes that force is torque. A couple of references. The videos came from Building the Body in Motion, Trail Guide to Movement. Some of the segment planes diagrams came from our Biomechanical Basis of Human Movement. The Hamel book, and then Marriott, which is our HAP reference as well.